In this video, I'll show you how to estimate a simple linear regression model using least squares. So for this example, we have a pizza restaurant chain, and it has 10 restaurants where the response variable, it measures the quarterly sales in thousands of dollars, and the X variable, the predictor variable, measures the student population in the surrounding area in thousands. And the idea is we want to see if there's a linear association between these two variables that will help plan where the restaurant builds its locations. So to estimate the simple linear regression model, which is of the form y hat equals b0 plus b1 times x. So b0 is the y-intercept, so the value of x, the value of y when x is 0, and b1 is the slope, so the rate of change in y per unit change in x. So we need to estimate b0 and b1, and the way that that's done is using a method called least squares. And we can think about that method if we look at this scatter plot over here. Scatter plot has the predictor variable, population, on the x-axis, and the response variable, sales, on the y-axis, and then the points are plotted accordingly. And this line here, this is the estimated simple linear regression line. And the way it's positioned is it's in such a way that the vertical distances between the points and the line, if you can imagine these vertical distances, some of them are bigger than others, like this is quite a big one, but this one is very small because it's almost on the line. So those vertical distances, when you square them and add them up, you get something called the sum of squared errors. And this line is chosen to minimize that sum of squared errors. And that's a mathematical problem that can be solved using calculus. And there's a formula for B1 and for B0. So let's have a look at the formula for B1. So it's the sum of x minus x bar times y minus y bar. So what is x minus x bar? X minus x bar is over here. It's the difference between x and the average of the x's. So 2 minus 14 minus 12, 6 minus 14 minus 8, and so on. And then y minus y bar is a similar thing for the response variable. So 58 minus the average of the y's is 130. 58 minus 130 is minus 72. 105 minus 130 is minus 25, and so on. If we multiply those two values together for each sample observation, we get x minus x bar times y minus y bar. So that's these numbers. And if we sum those, we get the numerator of this fraction here, which is going to calculate B1 for us. And then in the denominator, we get this value here, 568, which is the sum of x minus x bar squared. So it's these numbers squared. So minus 12 squared is 144, minus 8 squared is 64, and so on. If we add those up, we get 568, and that goes in the denominator. And in this example, that comes to 5. And then the y-intercept, so the formula for that is y bar, so the average response value, minus the slope estimate that we just calculated times x bar. And that gives us the y-intercept. And these two numbers tell us what the equation of this line is. The equation of this line is y hat equals 60 plus 5 times x. Every time x goes up by 1, y goes up by 5. And if we were to trace this line back to cross the y-axis, at x equals 0, it would cross at the value 60. And what I mean by y hat is that's the predicted value of y from this equation that we just estimated. And the reason it's called y hat is for notation, it's traditional to put like a little pointed hat over the y, and that tells us that we're predicting what y is. And so we're using this formula, y hat equals 60 plus 5 times x. So 60 plus 5 times 2 would come to 70. So that's the predicted value of y when x is 2. When x is 6, we get a prediction of 90, and so on. So these are all the predictions from the model. And you can see those on the graph. Let's focus on this one, 70. So when x is 2, which is down here, the actual value of y was 58, but the predicted value of y from the model is right on the line at 70. Let's see how XLStat estimates this model. So we'll select modeling data and then linear regression. And then we select our variables. So y is the response variable. That's this one. And then x is the predictor variable. That's this one. And we've got variable labels at the top of our selections. That's what these are. And let me just check on options, validation, prediction. Okay, everything looks fine. So let's just okay that. Because right now, oops, this selection is empty. What did I do? Prediction. I must have something selected that I shouldn't have. Maybe it's this button here. Yeah, there we go. I don't think that should be selected. Okay, now we're good. Okay, and let's just make that a little bit bigger so we can see it more easily. Once it's done thinking, here we go. Okay, and lots of output here, but I just want to focus on the equation of the line, which can be found in this part of the output here where it says model parameters. And intercept is 60. And then here where it says population X, there's the slope. And then it gives you the equation down here as well. Y equals 60 plus 5 times population. And hopefully it, well, it didn't give me, oh no, it did. It did give me a scatter plot. Okay, so here's a picture of the fitted model. So sales on this axis, population on this axis, and there's the data points, and then this solid line in the middle is the regression line. We won't talk about any of the other lines right now. We'll talk about those in future videos. But right now, that's what I want to focus on is the equation, and then actually we could talk about the y hat as well, because I think it gives me that in the output as well. Let's have a look at that. Yeah, here it is. So predictions in this graph here. So these are the predictions, 70, 90, 100. So these are what we calculated in this column. Okay, so that's how to estimate a simple linear regression model.